This is part 2 of my lecture on correlation and regression, and I'm going to be talking about correlation. Two variables are said to be correlated if they tend to change together, so that they can't be considered independently, because when one changes, the other changes as well. An example of that might be patients' height and weight, because tall patients tend to also be the heavier ones, whereas short patients tend to be the light ones. So height and weight change together. But correlation demonstrates an association between the variables, but it doesn't necessarily imply a causation. An example of that would be shoe size and hat size. For example, shoe size and hat size could well be correlated because people with large shoes tend to wear large hats because they are larger people. But it doesn't mean that wearing large shoes causes you to wear large hats, or even vice versa. It's just that they're both as a consequence of being a large person. So a correlation between two variables says there is an association between them, but it doesn't mean that that is a causal link between them, that one results in the other. It's just that the two tend to happen alongside each other. Scatter plots are a convenient way of showing this sort of data, and we've seen examples of these previously. Here's an example of a scatter plot showing weight in kilograms on the vertical axis and height in centimeters on the horizontal axis. On this plot, each point represents a pair of measurements xi and yi. We've used x for the height on the horizontal axis, so xi is the height of the ith patient. We've used y on the vertical axis representing weight, so yi is the weight of the ith patient. So every point is a combination of x and y, a pair of measurements representing a particular patient with a given height and a given weight. So the distribution of the points on this graph shows the distribution not only of x but also of y, height and weight. We already know how we can calculate the mean of a quantity, so if we take all the x measurements, or the heights, we can calculate the mean height, the mean x, which has the value of mx. But we can do exactly the same thing for the weights. Looking at the y values, we calculate the average of all the y's. The mean y is my on this graph. What we're interested in is correlation, is not just the mean x and the mean y, but how those two are related. And we do that using something called Pearson's correlation coefficient. So suppose that we've got n measurements of paired values x and y, that is xi paired with yi, for I going from 1 up to n being the last measurement. Then we can calculate the mean value of x and let that be mx, and the mean value of y, my. Then we already know we could calculate the variance of x as xi, that is the measurement x, minus mx, that is minus the average value of x, and square that deviation, add them all up and divide by n, the number of measurements, and that gives us vx, the variance of x. And we've seen that sort of calculation many times before. We know that if you want to do that in Excel, you can use the function varp to do it for you. But we can do exactly the same thing with y. If we take yi minus my, that is the y measurement minus the mean y, square that, add up all those deviations and divide by n, we get the variance of y. Exactly the same formula as the variance of x, just substituting y for x. And if you want to do that in Excel, the same function varp will do it if you give it the y data instead of the x data. Now notice in both of these formulae we've got either x minus its mean squared or y minus its mean squared. Squaring a number is multiplying by itself, so that is the x deviation times the x deviation, or the y deviation times the y deviation. But now we introduce a new quantity, the covariance, which instead of having the x deviation squared or the y deviation squared, is got the x deviation, xi minus mx, multiplied by the y deviation, yi minus my. So to calculate the covariance, we multiply the x deviation by the y deviation, add them all up and divide by n, and that gives us the covariance vxy. So it's exactly analogous to either the x variance or the y variance, but it's a mixture of the two, showing how x and y vary together. That's why it's called the covariance. And the function in Excel that will calculate that for you is called covar. What we're interested in is the correlation coefficient, which is given the letter r, and that's defined as vxy, that's the covariance, divided by the square root of vx times vy. That's another way of saying the geometric mean of vx and vy. The square root of vx times vy is the same thing as the geometric mean of vx and vy. If you look at these equations, you can see that if we had a perfect condition in which xi and yi were equal in every pair, then the formula for vx and the formula for vy would be identical if x and y are identical. But so would the equation for vxy if x and y are the same. So in this perfect situation where xi and yi change perfectly together, we get r is vxy divided by the geometric mean of vx and vy, which, if they're all the same, comes to 1. So r of 1 corresponds to perfect agreement between x and y. So that's why r is a measure of the correlation. It shows how x and y change together. And here we've got a scatter plot showing what is a perfect positive correlation between x and y. As x increases, y increases perfectly together. All of these points lie on a nice straight line. That's what we mean by a perfect positive correlation. R is plus 1 means that it's a line sloping upwards with a positive correlation. Here we've got a scatter plot with a positive correlation, but it's not perfect. As x increases, y tends to increase, but it doesn't do so on a perfect line. There's some scatter about the line. So we have a positive correlation. Certainly as x increases, y also tends to increase, but the correlation is not perfect. So r is positive, it's greater than 0, but it's not as big as plus 1, it's somewhere between 0 and 1. However, here we've got a situation where as x increases, y doesn't change at all. It just changes randomly. There's no tendency to increase or decrease overall. R is 0 here. There is no correlation between x and y. Here we've got a scatter plot with a negative correlation. As x increases, y tends to decrease, but it's not a perfect correlation. R is negative, meaning the line is sloping down, but it's somewhere between 0 and minus 1. But here we've got a perfect negative correlation. As x increases, y decreases, and it's on a perfect line, so we have r equals minus 1, a negative correlation. Now, to interpret the correlation coefficient, you'll find that sometimes the correlation coefficient r is quoted, and sometimes the square of the correlation coefficient r squared is quoted. You have to be careful to distinguish between them, because the range of r goes from minus 1 to plus 1, but r squared only goes from 0 to 1, because when you square a negative r, you get a positive r squared. So if y increases as x increases, that's a positive correlation, a positive value for r, and if y decreases as x increases, that's a negative correlation, and we have a negative value for r. But in both cases, r squared will be positive, because squaring a negative gives a positive. A perfect positive correlation has an r value of plus 1, and a perfect negative correlation has an r value of minus 1, but in both cases r squared is just 1. But if you have no correlation, then r is 0, and so is r squared. Quite often we'll want to know whether a correlation is statistically significant or not. So if we want to test whether a calculated correlation coefficient r is significant, we use a null hypothesis that there is no correlation between x and y. So as usual, we start with what we want to show, that there is a correlation, and take the opposite, that is the null hypothesis that there is no correlation. Then the appropriate test statistic is something called t, which is equal to r, the correlation coefficient, multiplied by the square root of n minus 2 over 1 minus r squared. When we've calculated t, we can test the value against the t distribution, and we have to use n minus 2 degrees of freedom. The minus 2 is because we've already calculated two means from our data, the mean of x and the mean of y, so we lose 2 degrees of freedom when calculating. You have to be careful when to use the correlation coefficient and when not to. The correlation coefficient that I'm talking about here is Pearson's correlation coefficient, and it's a parametric test, so it needs data to be quantitative and approximately normally distributed to apply a parametric test. If that's not the case, then the alternative is Spearman's rank correlation, which is a non-parametric equivalent of that, and that requires data that can be ranked in order, so it could be quantitative but not normally distributed, for example. The other thing to realize is that x and y should be different variables. If x and y are two measurements of the same parameter, then it's more appropriate to use the paired t-test rather than the correlation coefficient. We've already talked about the t-test in a previous lecture, so I don't need to repeat anything about that. But it doesn't stop you drawing the scatter plot, so even if the data represents two measurements of the same parameter, the scatter plot can still demonstrate that, but under those circumstances the correlation coefficient isn't appropriate, even if the scatter plot shows you what's happening. The other thing to be careful of is that x and y must represent the true range of the data relevant to the population that you're interested in. The measurement should be selected randomly from the entire range of your population rather than being selected. Otherwise, the correlation coefficient can be biased. Here's an example of the effect of using biased data. Supposing that we're interested in height and age, and we take the patients attending our children's nuclear medicine department. So here's a graph showing height varying between 100 and 170 centimeters for children of age between 5 and 16 years. And there it's a strong upward trend. The graph shows a strong correlation with an r squared of 0.87, showing that height increases with age in our children. But if we sample people attending the adult nuclear medicine department, we find that for the age range 20 to 70, there is no significant change of height with age. There is no correlation. The correlation coefficient r squared is only 0.07. It's quite close to 0. So for the adults, there is no correlation. But if we have a general nuclear medicine department that's taking children and adults, then sampling over the whole range gives us a result somewhere in between. The inclusion of some children gives us a weak correlation of height with age with an r squared of 0.71. So by choosing different populations, you can maybe change the correlation coefficient from a strong correlation to no correlation, when maybe the correct result is just a weak correlation if you sample over the whole range of the data. So that's the end of the second part of this lecture. In the third part, I'll do a worked example of correlation for you.